In this video, we will learn about the concepts of units, dimensions, and vectors, which is chapter 1 of class level physics. Let's start with the objects. After completing this entire lesson, we should be able to describe the scope of physics, nature of the laws and applications of principles of physics in our life. We need to be able to identify the number of significant figures in measurements and give their importance. Plus, we need to understand and distinguish between fundamental and derived quantities and give their science. We need to be able to write the dimensions of various physical quantities, apply the dimensional analysis to check the correctness of an equation, and determine the dimensional nature of unknown quantities. We need to differentiate between scalar and vector quantities, including giving examples of each type. We need to be able to understand and calculate the addition and subtraction of two vectors and how a vector can be resolved into its components and also how to calculate the product of two vectors. Right. Once we know the objectives, we are good to go. So let's begin. Let's start with physics. What is its scope? As we know, the scope of physics is very, very wide. Come to think of it, a vast variety of natural phenomena, including motion of objects. Let us say an ant is moving in a straight line. A vehicle is turning from right to left at a traffic junction. An aeroplane is taking off. That means it is going in a three-dimensional plane. Let's take another example from a different field of physics. When we talk of refrigerators, a gas stove, and the heat evolved, heat absorbed, etc., we are still talking of physics. Let's say we talk about rainbow and we talk about microscope, telescope, prism, etc. That is optics. We may think of what constitutes atoms and nuclei. We can also think about radioactivity and nuclear physics, both nuclear fission and nuclear fusion. We can think of electricity and magnetism. We can think of computers, electronics, communication devices, electromagnetic waves, and other modes of communication. So, as you can see, physics, the scope of physics is very, very wide. Now, we also need to understand that in physics, we study very, very large objects such as stars, planets, galaxies, etc. And at the same time, we also study very, very tiny objects like electron, proton, and other microscopic particles. And the macro and micro applies to the size of particles as well as to their masses. So at one end, the mass of the universe is about 10 raised to 55 kg. That means 1 followed by 55 zeros. That big a number. At the other end, the mass of an electron is very minuscule, 10 raised to minus 30 kg. That means 1 upon 1 followed by 30 zeros. So, physics is perhaps the basic of all sciences. It includes all the developments that are happening in engineering and technology because they are the applications of physics. Here are a few examples that can help us appreciate the scope of physics. We all know the story of a falling apple that has led to the understanding of gravitation. You might also know about electrical energy, how it is produced by hydro, thermal, or nuclear power plants. Let's understand the technology behind receiving messages and visuals from anywhere on the globe through wire and wireless communication media. Landing on the moon, study of planets and astronomy is also physics. At the same time, lasers and numerous applications of lasers. computers, electronics, high-speed computers. These are all part of physics. Now let's understand the nature of physical laws, the laws governing various phenomena that are occurring in nature, physical phenomena occurring in nature. Okay, what are the features of these physical laws? We can understand physical laws as conclusions based on repeated scientific experiments, not a one-off case. So scientists have performed and are performing to this day experiments repeatedly, recording the observations, and then understanding the cause and effect, which leads to universality of observations. So whether one is in America or whether one is in Australia, the principle of gravitation is applicable everywhere. Similarly, other principles of physics. So the principle of gravitation has led to the physical law which was formulated by Newton. Similarly, we can think of other physical laws such as law of buoyancy, laws of thermodynamics, laws of optics, such as the angle of reflection is equal to the angle of incidence. We might have studied that in our earlier classes. So, what is common with all these physical laws? They are true at least within their regime of validity. They are universal, as we discussed. They appear to apply everywhere in the universe. They are simple, they are not complicated, and expressed in terms of a single mathematical formula. For example, if we talk about force, force is nothing but mass into acceleration. Let's talk about gravitational force. So, gravitational force is nothing but it has a specific simple formula, which is nothing but force of gravitation is equal to G m1 m2 upon r square. So, we know that whenever any two objects are separated by, say, a distance which is r, and these objects have masses m1 and m2 respectively, then there is a force of gravitation which acts between them, and it is a universal physical law, and it is very simple to express. We will learn more about it in the gravitation chapter, but for now we can understand that force of gravitation is equal to G, which is a universal constant, multiplied by the product of the masses divided by the square of the distance separating. Okay. Similarly, we can also explain other physical laws in terms of simple mathematical expressions. Then the physical laws are absolute. Nothing in the universe appears to affect them. Okay. They are stable, unchanged since they are discovered, since the time they are discovered. Okay. Although they may have some approximations or exceptions, then they are omnipotent. Everything in the universe apparently must comply. So these are some things common to physical laws. Now let's understand what is the relation between physics, technology, and society. Well, technology is nothing but the application of the principles of physics for the manufacture of machines or gadgets and for the improvements or advancements. Here are a few examples, like different types of engines. Earlier there was a steam engine. Now we know about petrol engine, diesel engine, and other advancements. Similarly, means of communication, developing from radio, television, and all the way for today's mobile phones and laptops, etc. The generation of electricity, which is based on the principle of electromagnetic induction. Nuclear reactors, jet airplanes and rockets, X-rays, ultraviolet rays used in medical science, mobile phones, calculators, computers, lasers, etc. I hope we have understood the scope of physics, the laws of physics, what are common features of the laws of physics, and also what is the relation between physics, technology, and society. Now let's understand about the need of measurement. We can think of physics as a branch of science which deals with nature and natural phenomena. And for the study of any such phenomena, let us say gravitation, we need to measure quantities that are involved. For example, in this case, when we discussed about two objects separated in space, we have talked about the individual mass of each of the object and also the distance separating them. These are nothing but physical quantities and we need measurements. Okay. So the need for measurements. Why do we need to measure? Because we need to compare an object's physical properties with that of or those of other objects. Okay, that can help us explain the physical phenomena. So when we talk of, let us say, a car moving on the road, we will be interested in how fast it is going. So we need a measurement of time, and that also includes related measurements such as speed, distance covered, acceleration, etc. If we know the mass of a car, we can calculate the force of friction which is required if at all the car has to be stopped. Similarly, for all other physical phenomena, we need measurements. So, here, as we can see, to study the motion of a particle, we need to measure its displacement, velocity, acceleration, any instant. Similarly, measurement of time and distance has to be done. And in other scenarios, we may need measurement of mass, volume, temperature, etc. Okay. So, what comprises measurement? If I say the mass of this object, I will indicate a value, let us say 10, and I will indicate a unit, kg. So, measurement involves finding out a value and the relevant unit. Okay. Now, we can say measurement is the process of assigning a numerical value to a physical quantity. And what is a physical quantity? Okay. A physical quantity is any property of an object or a phenomenon that can be measured. We discussed certain examples like length, mass, time, temperature, etc. Now, what do we do in order to measure a quantity? We compare it with a fixed standard amount of that same quantity. And this standard amount is called. For example, when we measure the length of, let us say, a table, we do it with a ruler or a tape, then we are comparing its length to some standard unit of length. What is that standard unit? Let's say it is 1 meter. So what is 1 meter? This 1 meter is universally same. So there are certain standard dimensions which are considered universally same. We will come to those later in terms of length, mass, time, what are the standards. So against these standards, we measure, let us say, the length of the tape and how many times it is either bigger or smaller than the standard measurement. That will help us understand its value. For example, if I say a table is, let us say, 100, I'll just say, let us say table is uh, 1 meter long. Now, a table is 1 meter long means I am measuring this dimension with a ruler or a tape, right? Now, what is 1 meter means there is some standard length which has been assigned 1 meter, and this table is getting compared with this standard measurement. In this case, if the table is said to be 1 meter, means both these length, this length and this length are equal. If I say table is 2 meters, this length is two times or twice of the standard length. Similarly, if I say the mass of the table is 10 kg, then we are comparing this with a standard for 1 kg. We are saying this table is 10 times heavier than the standard of 1 kg. So again, to reiterate, to measure a quantity, we compare it with a fixed standard amount of that same quantity, and that standard amount is called a unit. Okay. Now, we need to know that there are various systems of units of measurement that have been developed historically. As you can see in Indian tradition, there were measurements which are indicated in the document you can see in front of you. Then globally also there were certain units of measurement, and three common units of measurement come to mind, which are the NKS, the CGS, and FPS systems. So these measurement systems have been based on the units of measurement of length, mass, and time. Let's understand. So MKS, M stands for meter, which is a unit of length. K stands for kilogram, short form kg, which is a unit of mass. S stands for second, which is a unit of time. Here again in CGS, C stands for centimeter, which is a length of time. G stands for gram, which is a unit of mass, and S stands again for second, which is a unit of time. In FPS, F stands for foot and P stands for pound. Foot is a measurement of length, pound is a measurement of mass, and S is again a measurement of time, which is second. Three different systems. So scientists wanted to have a uniform system of measurement throughout the world, and that's how SI system, which is short form for System International de Unites. It's a French word. It evolved, and it has been accepted worldwide as the standard system of measuring physical quantities. And as you can see on the screen, there are seven physical quantities mentioned, and their units in SI are mentioned side by side. Okay, for example, length. The SI unit is meter, mass, kilogram, time, second, electric current, ampere, temperature, Kelvin, luminous intensity, candela, amount of substance, mole. Now, we can find out the relation between each of these SI units with the earlier units. For example, when we say meter, NKS system also has meter, so they are same. CGS system has centimeter. We know that 1 meter is equal to 100 centimeters. So anything measured in the CGS system in terms of length can be converted into the SI unit of meter. Similarly, CGS unit and NKS unit are kilogram and gram as the mass, and SI unit, the kilogram is the unit of mass. So for NKS, it is same, but for CGS, we know that 1 kg is equal to 1000 grams. And similarly, the time is seconds for either the SI system or NKS or CGS. So there is no need of, you know, arriving at a separate value. We all can understand a second as the same unit for different systems. Now let's understand the foot, pound, and second. Second again is same in FPS. We need to see what is 1 foot in terms of the standard SI unit of 1 meter. So 1 foot we know is nothing but 12 inches, and each of the inch is equal to approx 2.54 centimeters. So 12 inches will translate to 12 into 2.54 centimeters. So 1 foot is equal to 12 into 2.54 centimeters. And we know that 1 meter is equal to 100 centimeters, or 1 centimeter is equal to 1 by 100 of a meter. Right? So 1 centimeter is equal to 1 by 100 of a meter. And we can understand 12 into 2.54 centimeters is equal to 12 into 2.54 into 1 by 100 of a meter. So this is equal to 1, right? Now what is this value of rocks? This value comes out to be around 0.3048 meters. So 1 foot can be approximately said as 0.3048. Similarly, pound is a unit of mass in the FPS system. So 1 pound is equal to approx 0.4536 kg. This is how we can convert the values, measurement values from one system of unit to another. Okay. Now let's understand what is meant by the statement SI system is a metric system. This means that the smaller and larger units are always submultiples or multiples of 10. Okay. So if we talk about the SI units, we know that for length, the SI unit is meter, right? And for larger units of length or measurements of length, we know we have something called as kilometer, which is nothing but 1 kilometer is equal to 1,000 meters. It's a multiple of 10. We can also write it as 10 raised to 3 meters. Similarly, still larger distances like megameter. Okay, it is nothing but 1,000 into 1,000 meters, which is nothing but 10 raised to 6 meters. 1 gigameter is equal to 1,000 into 1,000 into 1,000 meters, which is 10 raised to 9 meters. So all these are multiples of 10. Similarly, for shorter units, we know 1 centimeter is equal to 1 by 100 of a meter, which can be written as 1 by 10 raised to 2 of a meter. And when we have 10 raised to 2 in the denominator, it can be written as 10 raised to minus 2 when it comes to the numerator. Similarly, we have 1 millimeter is equal to 1 by 1000 of a meter, which can be understood as 10 raised to minus 3 because it is 1 by 10 raised to 3 meters. 1 micrometer short form we write as mu is a Greek symbol. It's understood as 1 micrometer, it's still smaller unit. It is nothing but 1 by 1000 into 1000 meter, which is nothing but 1 by 10 raised to 6 meter, which is 10 raised to minus 6 meter. 1 nanometer is equal to similarly 10 raised to minus 9 meter, and so on. These are all submultiples of. That's why we say SI unit is a metric system. Okay. Now, here are some of the prefixes for smaller units of measurement, and similarly for larger units. Okay, the prefixes you need to remember. For length, they are there's the suffix meter comes. For mass, the suffix kilogram comes, and so on. Okay. Now, here are some order of magnitudes of very small quantities as well as very large quantities, just for informational purpose, and similarly on a time interval level. Now, as we discussed a short while ago, when I say an object is 5 kg, I am comparing that object with a standard unit of kilogram. So, there was a particular cylinder made of platinum iridium alloy, okay, whose mass has been considered as 1 kg. And when I say any other object, let us say is 5 kg, it means I am saying that object is 5 times heavier than the standard. Similarly, the standard unit of length has been defined as 1 meter, which is distance traveled by light in this time interval. So how do we arrive at it is, we can understand that light travels at the speed of 3 lakh kilometers per second, right? So light covers 3 lakh kilometers and it takes only 1 second time for that. This can be translated into light is covering 3 into 10 raised to 5 kilometers, because there are 5 zeros in 1 second. We can also understand it as in terms of meters, 3 into 10 raised to 5 kilometers, and each kilometer is equal to 1000 meters, that is 10 raised to 3 meters. So overall, these many meters light travels in 1 second. Correct? Now, we want to see what is the definition of 1 meter. So, let us say I write in 1 second, distance traveled is 3 into 10 raised to 5 into 10 raised to 3 is 10 raised to 8 meters. So, 1 meter is nothing but 1 upon 3 into 10 raised to 8 meters. Seconds. Because this seconds is on the, I write it seconds here. Seconds is on the left side. Okay. That means I can define meter as some distance traveled in this time interval. and that is what is mentioned here. So 3 into 10 raised to 8 is approximate. Here, if you see this 299,792,458, it's just an approximate. You can say it is 2.998 into 10 raised to 7. Sorry, 10 raised to 8. So let's write it. 1 by 299,792,458 is, I think, what? 1 point, if I put a decimal here, 2.9979. Okay. If I put a decimal after 2, it means after that there are 8 digits, so it is 10 raised to 8. This is an approximate figure, this is the actual figure. So 1 meter has been defined as this, as a standard. Later on, it has been, further refined, and 1 meter now, 1 second is now defined as the time required for a particular isotope of cesium atom. We'll understand isotope later. So time required for this particular isotope to undergo these many vibrations between two fine levels. We will understand this in more detail when we discuss about atoms and nuclei further down, like, okay, in the atoms and nuclei units. So for the purpose of our understanding till now, we have physical quantities, we measure them, that means we assign a value and a unit to them. How do we arrive at the unit? We are comparing the measurement with some standard unit of measurement, and we have three different traditional units, and the standardized unit is SI, and SI is a metric system of units. Okay. Now, in the next video, we will understand uh, the importance of significant figures. I hope you understood till here. Please revise this concept from the starting of this chapter till this page number 8 to understand and absorb the learning.